Hello everyone, and welcome to the concluding video for Chapter 2. We're not spending very much time in Chapter 2, we're only doing sections 2.1 and 2.2. So this video is on section 2.2, which gives a definition of power inside of a weighted voting system. So Chapter 2, of course, is longer than what we're doing, but I like section 2.2 as a conclusion because it gets at the heart of what you'd want to know about a weighted voting system. When different voters have different weights, when they have different amounts of votes, a natural question to ask is, can we quantify how much power somebody has? And that's what we're going to do in section 2.2. So here's some motivation for what we're going to do. And here are a couple of examples from last time. So the point of both of these examples is that players' weights can be deceiving. So in this first example, this is the same example we had with the business partnership where we had 4 players and these were the different weights. So let's consider this voting system for a second. Remember what this means. This means that there are 4 voters and voter 1 controls 8 votes, voter 2 controls 7 votes, voter 3 controls 3 votes, and voter 4 controls 2 votes. And anytime a motion is put forward, you need 19 votes to pass that motion. That's what this notation means. You have 4 voters or 4 players, whichever word you'd like to use, and these are the amount of votes that each player controls. This is the amount of votes that a motion needs to pass. Okay, so in this system, notice that there are 20 total votes on the table. There are 8 plus 7 plus 3 plus 2 votes. So the 4 voters together have 20 votes. And notice that you need 19 votes to pass. And 19 is pretty close to 20, right? So you need most of the votes in the system to pass. And in particular, think about what it would take for a motion to pass in this system. So suppose for a second that player 1 and player 2 get together. So that's the 8 and the 7. Do they have enough power to pass a motion? Well, the answer is no, because they control 15 votes between the two of them, and 15 votes is not enough to pass anything, because 15 is smaller than 19. So what if player 1, player 2, and player 3 all get together and they decide to try to pass a motion? Do they have enough power between the 3 of them to pass a motion? And the answer again is no. Between the 3 of them, they control 18 votes, and 18 votes is not enough to pass a motion because 18 is smaller than 19. So really, in the system, what you need is all 4 players together have to vote yes on a motion in order to pass it. So in other words, a motion passes if and only if the vote is unanimous. You need all 4 players to agree to pass something. So in this system, actually, every player has the same amount of power, right? In a unanimous system, a system in which you need unanimity, it doesn't matter that player 1 has 8 votes and player 4 only has 2 votes. A measure only passes if all 4 players agree. If any one of the players decides not to, then the motion won't pass. So the point of this first example is to illustrate that even though you have radically different weights, so notice that player 1 has quadruple the weight of player 4, right? He has 4 times as many votes. That doesn't really matter. They have the same amount of power. They have the same amount of ability to pass a motion as anybody else. So in this voting system here, all 4 players have the same amount of power, even though the weights are different. By contrast, consider this example that we looked at last time. In this example, remember that, so what was the point of this example? So the 4 players all have approximately the same amount of votes, right? 10, 10, 10, and 9. But remember, player 4 actually had no power at all. In this weighted voting system, all that matters are the opinions of the first 3 players. Okay, so if you don't remember that, see the last video, but that was part of the point of this example, that player 4's opinion doesn't really matter. If a motion is going to pass, it doesn't matter whether or not he agrees with it, and he can't bring a motion down by himself. So player 4's opinion is irrelevant. Notice, though, that player 4's weight is basically the same as the other 3 players' weight. Even though he has approximately the same weight, he has no power compared to everybody else. Okay, so these 2 examples illustrate 2 extremes. In the first example, the weights of the players are very different, and yet the power that each player has is really the same. In this example, the weights are basically the same, and yet the amount of power shared by the players is much different. The amount of power that player 4 has is much different than the amount of power player 1 has. Player 4 has no power in the system. The other 3 players have the same amount of votes, so they share the rest of the power amongst themselves. So player 1 has a third of the power, player 2 has a third of the power, player 3 has a third of the power, and player 4 has none of the power. So the goal of this section is to develop a formal definition of power that can deal with these sorts of extremes, that can deal with the fact that weights can be deceiving. And we study how we can measure it. So in this system here, player 4 has no power, as we just discussed. So we can sum up the discussion about that example by giving a list of numbers, percentages or fractions. And the list of numbers is telling you how powerful each player is relative to the others. So in this list of number here, we're saying that player 1 has 33% or a third of the power, player 2 has 33% or a third, and player 3 has 33% or a third, and player 4 has 0% or none. Okay, so that's the goal of this section. We want to actually develop a definition of power and make sure that that definition corresponds with how power plays out in examples like this. Okay, so more formally, here's what we're going to do. Given a weighted voting system, that's given by this, a quota and the n weights for the n players, assign a number, beta sub I, to each player that measures the power of that player in the system. So we're going to give a list of numbers so that the first number in the list tells you how powerful player 1 is, the second number in the list tells you how powerful player 2 is, etc., all the way up to player n, and beta n will tell you how powerful player n is. So that's the goal. Before we do that, though, let me start with a wrong definition of power, or a naive definition, however you want to say it. It's a natural and intuitive definition. It just doesn't give us the notion of power that we know to be accurate in reality. So, yeah, let me just give you a motivating example here. Think about this example. Quota is 8. There are 4 players. Player 1 has 5 votes, player 2 has 3 votes, 3 has 2 votes, and player 4 has 2 votes. Here's one way you could think about a player's power. You could say to yourself, okay, there's 5 plus 3 plus 2 plus 2 equals 12 total votes in the system. Okay, there are 12 total votes on the table. Player 1 has 5 of those votes, so it stands to reason that he has 5/12 of the power. Player 2 has 3 of those votes, so it stands to reason that he has 3/12 of the power, and so on. This is certainly a reasonable thing to do, I suppose. The question is this really, though, a good notion of power? And the answer is no. In this system here that we've just considered, right, 30, 10, 10, 10, 9, if you use that definition of power, you would say to yourself, okay, there are 39 total votes. Player 4 controls 9 of them, so we'd say that he has 9 over 39, or 23% of the power, if you were to use a definition like this. But we already saw that player 4 has no power. So how could he have no power and have 23% of the power, right? It makes more sense to say that his power is 0%. So this definition just doesn't work, okay? So I show you this definition, this bad definition, for a couple of reasons. First of all, the definition that we're going to give is more complicated than this, but the reason it's more complicated is because it's more sophisticated, and it really does get at the heart of what it means to be powerful, what it means to have power. Also, I show you this example because even when I don't show students examples, they'll come up with this notion of power on their own on an exam when they don't know what to do. Okay? So I'm just warning you ahead of time, don't do this. This is the wrong notion of power. So if you don't know what to do on an exam and you find yourself doing this, you can at least know you're making a mistake. Using this method will almost never give you the right answer. So before I give you the real definition of power that we're going to use, I need to give you some basic terminology, some setup terminology. And the first word is a coalition. So a coalition, just like in colloquial English, is basically just a group of people that get together. So here, a coalition is any set of players who might join forces and vote the same way. And so they don't vote the same way all the time, necessarily. They just on a particular motion, they might vote the same way. And a coalition can just be a single person. It can have 2 players, it can have 3 players, and so on, all the way up to all of the players. So if every single player in the system decides to join forces, that's a coalition, and the technical term for that is the grand coalition, when everybody's on the same side. Okay, so we'll denote a coalition with set notation, so this is nothing fancy. It's just saying that this set here consists of the 3 players, player 1, 2, and 4, so it's the coalition consisting of those 3 players. So we're going to be interested in a particular kind of coalition, and we're going to call that kind of coalition a winning coalition. So just notice that some coalitions have enough votes to win, and some do not. The former kind of coalition is called winning, and the latter are called losing. So if you form a coalition and there are enough votes inside that coalition to get a motion to pass, that's called a winning coalition. If you don't have enough votes inside your coalition to pass a motion, that's called losing. So here's a small example. The quota is 10, and there are 4 players, and here are their weights. So the first question that we can ask is P1, P4 a winning coalition? If you want to answer this question, just add up the weights of player 1 and player 4, and so player 1 controls 7, player 4 controls 2, so between the 2 of them, they control 9 votes, and 9 votes is not enough to pass a motion. You need 10 votes to pass something. So no, this is a losing coalition here. There is not enough votes between the players to pass a motion. On the other hand, this coalition is winning. Okay, if you add up the weights of these 3 players, you do 5 plus 4 plus 2, you get 11. 11 votes is enough to pass a motion because 11 is bigger than 10. So that's the idea of a winning coalition. The next definition is a critical player. So once you have a winning coalition in front of you, a player is said to be critical in that coalition if the coalition must have that player's votes to pass the motion. In other words, if you kick that player out of the coalition, then the coalition is no longer winning and is now losing. So the player is critical if he or she really is needed to pass the motion. So let's consider this coalition, P1, P2, P4, in this weighted system where the quota is 13. So the question is, who are the critical players inside this coalition? And I should first point out that to even ask about critical players assumes the coalition is winning. Okay, you don't need to consider losing coalitions at all. Nobody is critical inside a losing coalition. The coalition just loses and you move on. So notice that this coalition here is winning. P1 controls 7, P2 controls 7, P4 controls 2. And so the sum of their votes is, what, 16. So they have enough votes to pass a motion if they want to. Therefore, this is a winning coalition. So now let's ask, inside this particular winning coalition, who is critical? Well, to answer that question, just ask yourself, for each of these players, if I kick him or her out, does the coalition stay winning or not? Oops. Okay, so first ask yourself, player 1, is that player critical? If I kick him out, will the coalition still be winning? Well, no, the coalition wouldn't be winning if you kicked player 1 out, because if you kick him out, all that's left is player 2 and player 4, and the sum of their votes is 7 and 2, which is 9, and 9 is smaller than 13. So if you kick player 1 out of there, the coalition doesn't win anymore. They can't pass a motion anymore. So player 1's votes really are necessary for this coalition to be winning. And the same goes for player 2, because he controls 7 votes. Player 2's votes are necessary for this particular coalition to be winning. Notice that player 4 is different, though. If you kick player 4 out, he only controls 2 votes. If you kick him out, player 1 and player 2 have 14 votes between them. If 14 is bigger than 13. So the coalition is still winning if you throw player 4 out of there. So player 4's votes were not necessary for this coalition to be winning, so player 4 is not critical. So the first 2 players in this coalition were critical, and the third one was not. So that's what it means to be a critical player. Okay, last definition before we move on. A player's critical count is simply the number of times that player is critical. So in other words, to figure out the critical count, you count the number of winning coalitions in which that particular player is critical. And this number is called the critical count of that player. So if you're ever asked to compute the critical count of a particular player, what you have to do is you have to figure out how many winning coalitions contain this player such that that player is critical in those coalitions. So count the number of winning coalitions in which that player is critical. So let's do this. Let's find the critical count for each player in this system. 4:321. Well, if you want to do that, the first thing you have to do is list all of the winning coalitions. And I've done that for you. P1, P2, P3 is winning, right? That's 6 votes, and 6 votes is enough to pass. P1, P2 is winning because 3 plus 2 is 4. So 3 plus 2 is 5, which is bigger than 4. And P1, P3 is winning because 3 plus 1 is 4. So P1 and P3 have enough votes to pass a motion if they want to. So now inside of each of these winning coalitions, let's decide who's critical. So let's start with this first one. If you throw P1 out of there, is the coalition still winning? Well, the answer is no. If you throw P1 out of there, P2 and P3 do not have enough votes to pass this motion. They only have 3 votes between them. So P1 is critical here. In this coalition, player 1's votes are necessary. What about player 2? Are his votes necessary? Well, if you throw him out, P1 and P3 have enough votes between them to pass the motion. So P2 is not necessary. You can throw him out and the coalition is still winning. So player 2 is not critical there. Player 3, by the same token, is also not critical. You can throw him out and the coalition is still winning, and so on. So you can go through and underline, this is what the book does, for each winning coalition, underline the player that's critical inside that winning coalition. So notice in this second coalition, P1 and P2, if P1 is kicked out, the coalition is no longer winning because player 2 does not have enough votes by himself to pass a motion. And if you kick out player 2, player 1 does not have enough votes by himself to pass a motion. So in the second coalition here, both players are critical, and by the same token, both players are critical in this third coalition. Okay, so if you want to compute the players' critical counts, once you've done this work here, where you've listed all the winning coalitions, and you've underlined each critical player inside each winning coalition, all you do now is count the number of times you underlined each player. So player 1 was underlined 3 times, so his critical count is 3. Player 2 was underlined 1 time, so his critical count was 1, and player 3 was underlined 1 time, so his critical count is 1. So at this point, I've thrown now 4 definitions at you, and they're maybe not terribly intuitive. These definitions can take some getting used to, right, of critical count, critical player, etc. So before we go on, though, you must understand these definitions. So if you don't understand this, you need to either read through the book or email me or whatever. I mean, you should be reading the book anyway, but if you don't understand what's happening now, you won't understand our definition of power, which is coming in a second. So make sure you contact me or you email one of your classmates or whatever it is you do, but make sure you understand this, because our goal is to get a definition of power going. And if you don't understand what we just did, you can't understand the definition of power. So speaking of a definition of power, here it is. Let P1 up to Pn be players in a weighted voting system, and let B's, capital B's, denote the critical counts of each player. So B1 is the critical count of P1, B2 is the critical count of player 2, etc. And so keep in mind what these numbers represent. B1 is the critical count of player 1. What that means is B1 is the number of times player 1 was critical, right? The number of winning coalitions in which player 1's votes were necessary. Same for B2, same for all the way up to Bn. Let's let T represent the sum of all these numbers, the total critical count. So once you have all the critical counts done and listed, just add all them up to get the total. Okay, so here now is the definition of power. The Banzhaf Power Index, which is just a fancy way of saying power, and it's named after Banzhaf. So this is Banzhaf's, he's a mathematician, it's his notion of power that we're using right now. So the Banzhaf Power Index of player I is defined as his critical count divided by the total critical count. Okay, that's what power means in this particular section. Okay, so we now have a definition of power, and we can now, given a weighted voting system, give the power of each player. So let's do that. Before we move on, though, this is just fancy terminology here. The Banzhaf power distribution is just a list of the powers of all of the players. So when somebody gives you, excuse me, when somebody gives you a weighted voting system and asks for the Banzhaf power distribution, they are just asking you to find the powers of all of the players and list them. Okay, so let's find the Banzhaf power of each player in this weighted voting system. We already got started on this system. So let me just lay out the steps of what you need to do if you're going to compute the power of each player. The first thing you must do is make a list of all possible winning coalitions. The second thing you must do is determine who's critical inside of each coalition and underlining like we've been doing. The third thing you need to do is find the critical counts. So you're doing steps 1 and step 2 so that you can do step 3. You must know the critical counts before you can do anything else. Once you have the critical counts, you now compute their total, so just add all of them up. And as a last step, you compute the power indices themselves. You compute the power of each player, and you do that by taking the respective critical count and dividing by the total critical count. So the idea here is that T is sort of the total power inside of the system, and when you're doing this B1 divided by T, B2 divided by T, etc., you're dividing that power up amongst the players. So B1 over B1 divided by T is the fraction of power that player 1 has. B2 over T is the fraction of power that player 2 has, etc. Okay, so on the next slide, we're going to actually find the Banzhaf power index of each player in the system, as it asks us to do. But remember, we've already done steps 1 through 3. We found the critical counts. So I'm not going to do that again. I'm just going to give it. So the critical count of player 1, remember, was 3, and then P2 is 1, and P3 is 1. So the total critical count is just the sum of those numbers, which is 5. So T in this particular example is 5. Well, once you have the critical counts and once you have the total, to find the power of each player, just take his critical count and divide by that total. So the power of player 1 is 3/5. So in other words, in plain English, what we're saying is that player 1 has 60% of the power in this system, according to Banzhaf. And Banzhaf is misspelled, but whatever. And player 2, well, his power is his critical count, which is 1, divided by the total. So the Banzhaf power for player 2 is 1/5, which is 20%. So player 2 has 20% of the power, and by the same token, player 3 has 20% of the power. So there are a few things that you can think about if you're thinking about what this means. And notice that in this system, 4:321, player 2 has twice as many votes as player 3, right? 2 is twice 1, and yet they have the same amount of power. Okay, so player 2 having double the votes of player 3 doesn't really help player 2 relative to player 3. Their power is the same. And by the same token, player 1 doesn't have triple the amount of votes as player 2, right? 3 is not triple 2, but player 1 has triple the power of player 2. Right, because 60% is triple 20%. So these power numbers are not obvious just given this system, right? Just given the system, you might think that player 1 is 3 times as powerful as player 3. And player 2, or sorry, player, what did I say? You might think that player 1 is 1.5 times as powerful as player 2, right? But he's actually triple as powerful. And you might think that player 2 is twice as powerful as player 3, but that also is false. Right? So the weights here can be slightly deceiving in terms of who actually has power relative to everybody else. Okay, so this is how you actually compute the power of a player inside of a weighted voting system. Okay, so I want to end with an example from your book that's really nice. And the reason I'm showing you this example is to show that this notion of power is not just some sort of idle mathematical speculation that mathematicians just do when they're bored, right? This kind of thinking has applications to real-world voting. I mean, of course it does, because as we saw in the first section, there are all sorts of systems out there that use weighted voting. The United Nations is one of them, the Electoral College is another, business partnerships, corporations, etc. These weighted voting systems are all over the place, and so once you have a system in place like that, it's nice to know who has the power and how much power do they have. So here is a really cute real-world example from the 1960s that I want to walk us through. It's an example from New York State. And so back in the 1900s, county boards in New York operated as weighted voting systems, and the reasoning was not unreasonable, I suppose. Counties are often of uneven size, so people argued that proportional representation in this form, in the form of a weighted voting system, was appropriate. So here's an example from the 1960s. This is Nassau County, and it was divided into 6 districts. And here are the weights of the given districts, and these weights are based on population. So, 28, what is that, 14 times 2? So presumably Oyster Bay had 14 times as many people as Long Beach, for example. So before we move on, I want to make sure that what this table is telling you is clear. Oyster Bay has 28 votes. That does not mean that they have 28 representatives, all of whom can vote however they feel like. Okay, what this is saying is that Oyster Bay controls 28 votes, but all 28 votes are going the same way. Okay, so this is not representative in the form of like a House of Representatives. Okay, it really is a formal weighted voting system. Glen Cove has 2 votes, and both of those votes will go the same way. So, in the 1960s, the quota was just a simple majority. So let's set up a weighted voting system, and then let's compute the power indices. So if you want to know the quota, which is something you would have to know to set up a weighted voting system, you need to know what the simple majority is. And so notice that in the system, if you add 31, 31, 28, 21, 2, and 2, you will get 115. Since you're interested in a simple majority, you take that 115 and cut it in half, and you get 57.5. But remember, you can't have fractional amounts of votes, so the quota is 58. That's what a simple majority is in this system. Okay, so remember, you always round up if you get a fraction. So the quota is 58. Now, the book does a really good job explaining this, and I'm running short on time. So I'm not going to go into how you actually compute the power indices. I will just, or indexes, whichever the proper plural is. So I will just leave it to you to read that in the book. But here actually is the Banzhaf Power Index. H1, H2, and H3, the top 3, have BPIs of 33%, or a third. And Oyster Bay, North Hempstead, and yeah, I left North Hempstead off here by accident, but excuse me. Okay, so I see what I've done here. There is no H3, of course. H3 should be Oyster Bay. Excuse me. So the top 3 have a third of the power. Okay, so that H3 should be an OB, and this OB should be an NH, right? So the big picture of this example, and forgive my typo here, but the big picture here is that the top 3 players here, the top 3 districts inside this county, each have a third of the power. The bottom 3 districts have no power. Okay, so if you actually list out all the winning coalitions and do the critical counts and everything that's needed to compute the power indexes, you will see that Glen Cove, Long Beach, and North Hempstead are never critical. Their critical counts are 0, which means that their power is also 0. So the word to use here is that the districts are dummies. These 3 smaller districts are dummies. They have no power. And notice that North Hempstead actually has quite a few votes. 21 votes is not that far from 28. And yet Oyster Bay has a third of the power and North Hempstead has none of the power. Okay, so again, I will leave the computations to you, but make sure you understand the big picture of what I'm trying to tell you here. The top 3 players are the only players with power, and they split the power equally. They each have a third of the power. The bottom 3 players have no power. They're dummies. Their BPI is 0. Okay, so what makes this example interesting is that Bontoff, he ran the computations himself, and he made the case that what was happening to the smaller districts actually violated the Equal Protection Clause of the 14th Amendment of the Constitution. He said, in court, he said, look, these people, this county has set up a system in which these 3 districts essentially are unrepresented, right? They have 0 power. So it's almost like having no representatives at all. It's equivalent to that. So he went to court and he made that argument. He told the judge, this is my notion of power, and here's why I think this notion of power is correct. And given my definition of power, these 3 districts have 0 of it. Okay, and that's not fair. It violates the Equal Protection Clause. So because of this analysis, in 1993, which wasn't that long ago, right, just 21 years ago, a federal court actually made it unconstitutional for county boards to use proportional representation as the basis of a weighted voting system. Okay, so once you have a notion of power in place, which Bontoff did, right, in terms of critical counts and the total critical count, etc., once you have that notion in place, you can have real-world effects like this. Once you can quantify power, you can actually point out, oh, these people over here actually have 0 power in the system you've set up, and that's not fair. Okay, so that's all I had to say about Bontoff power.